we talked about some rules for differentiation. This is what we did last time. And we talked about the derivative of a power. I'm going to use the prime notation now. Derivative of x to the n is n x to the n minus 1. And that was kind of the fundamental starting point. We also said that the derivative of a constant is 0. Now, if f is differentiable, then the derivative of a constant times f was equal to the constant times the derivative of f. That was the constant multiple rule. And then if we know that f and g are both differentiable, then the sum is differentiable, and the derivative of the sum is the sum of the derivatives. And we also said that because of this, the same rule holds for the derivative of a difference of two functions. And then we had the product rule. So the derivative of f times e. And the derivative of the product is actually the sum of two terms. The first term being f prime of x times g of x, and the second term being f of x times g prime of x. And finally, we looked at the quotient rule. The derivative of a quotient, f of x divided by g of x, will be a quotient where the numerator is f prime g minus f g prime over g squared. And recall, there's no derivative here, it's just g. Okay. So this is what we have. These are the shortcuts, so to speak, for taking derivatives rather than using the definition every time.
I learned this before with the u prime v. Would we be able to use that notation?
Yeah.
Okay.
He's referring to if u and v are functions, then the derivative of u times v would be u prime v plus uv prime. And this is common in some textbooks. Similarly, for the quotient rule, u prime v minus uv prime over v squared. Okay? All right. So let's take an example and try to use some of these. Let's find the derivative of this function. X plus 1 times 2x minus 4 divided by x plus 1. Oh, sorry, x squared plus 1. So we look at this function and we see that this is a quotient of two functions, right? So we're going to be using the quotient rule. You can think of this numerator as f and this denominator as g. And just using prime notation, let's write the denominator first. The denominator would be the square of the old denominator. That's our g squared. So, and then here we have f prime g. So f prime. So take the derivative of the numerator, which I'll just write as the numerator prime. Okay, times the denominator minus the numerator, let's just write n, times the derivative of the denominator. So that would be x squared plus 1 prime. Right, this is just writing the rule, putting primes where derivatives should be. So now in computing this, we have to do the prime here and the prime here. The derivative of this bracket quantity requires us to use the product rule, right? Does that make sense? Okay. So, and the product rule is going to, this is going to turn into 2 more terms, and that's pretty long. So at some point you have to decide whether it's wise to use the rule or to turn it into a simpler expression and use a simpler rule. Okay? In other words, this is a product of 2 functions. Is it worth using the product rule? Or can we just multiply these real quick and take the derivative? Probably multiplying would be better, right? It will require less simplifying. So if you multiply those 2, we can do that here, then you get 2x squared plus minus 2x, right? Minus 4. And that's the product here. And now we can do the derivative. What would be the derivative here? 4x minus 2. So that takes care of that, so we don't even have to do the product rule, which would have taken quite a bit of space. Minus x squared plus 1 minus, so the numerator, we could probably work that out, right? That's 2x squared minus 2x minus 4. And what's the derivative of x squared plus 1? Just 2x over x squared plus 1 squared. Okay? And that's the answer. Okay? Now, if our question is just find the derivative, then that's fine. But later on, we're going to find the derivative, and we're going to have to do some more work with it, in which case simplifying is necessary. But at this point, I'm just going to leave it like that. But the point I want to really drive home right now is that these rules are nice shortcuts and they're wonderful. But it's important to know when to use them and when not to. Here's another example. Something similar. Say you have x plus 1 times 2x plus 1 over x squared. It looks like a quotient. It is a quotient, so we could probably use the quotient rule. But again, we get something really, really long and complicated. Since the denominator is a single term, it might be better to first simplify this before we do the derivative. So this is just 2x squared plus 3x plus 1 divided by x squared. And then we can divide by x squared very easily. Does that make sense? And now we can just use the power rule, because each term, so that would be y equals, what's the derivative of this? 0. This would be negative 3, x to the minus 2, minus 2, x to the minus 3. Does that make sense? So that's the derivative. Okay, much simpler than using the quotient rule. So try to look out for things like that. Whatever would simplify and speed up your work would be nice. Okay. So this was just a quick review of what we had so far. The next topic is to learn how to do derivatives of trigonometric functions. Okay. We're going to need some trig identities, so let me write it down. Sine of x plus y is sine x cosine y plus cosine x sine y. Is that right? And then cosine of x plus y is cosine x cosine y minus sine x sine y. What is so special about trigonometric functions? What types of functions are trigonometric functions? They repeat their values, right? What is that called? Do you remember? Periodic, right? They're periodic, they're circular functions. They repeat. So, for example, if we have the graph of sine x, we know that the graph lives between 1 and negative 1. And the fundamental period of sine is 2 pi. And so and it repeats that way, right, forever. That's the graph of sine x. When we do the derivative of sine x, what we're actually computing is the slope function for sine x. Okay? So let's see what we can find out about the derivative without doing any calculations, just based on the graph. We can tell that the slope at this point is what? 0, because it's got a horizontal tangent. So the slope is 0. So we know the derivative has to cross that point. And the slope is 0 here as well, right? Okay. How about the slope here? If I draw a tangent line, what does that tell you? Negative. So maybe something down here. What about the slope here? Positive. So maybe something up here. Okay? But then those points, those values will repeat, because just like the curve is periodic, means the tangents are periodic, right? So the derivative is expected to be a periodic function, so it's probably going to be a trigonometric function, right? Anyway, so having said that, let's actually do the computations. So if I want the derivative of sine x, then I don't know anything but the definition. So I could say this is the limit as h goes to 0 of the difference in y, so sine of x plus h, minus sine of x over h. You remember that? Okay. Let's see what that leads to. Well, sine of x plus h, from that formula over there, we know that it's sine x cosine h plus cosine x sine h minus sine x over h. And then we see that this term and this term have a common factor, right? What is that common factor? Sine x. So, and if we just look at this term by itself, do we see anything familiar? Sine h over h as h goes to 0, right? So let's separate that. Let's see. So I'm going to get sine x times cosine h minus 1, right? I'm factoring out sine x over h, plus the limit as h goes to 0 of cosine x times sine h over h. Is that clear? Mm-hmm. Okay. Why did we choose to separate it like this? Well, because the limit of this quantity and this quantity is known from previous theorems, right? So this is equal to, well, sine x is a constant. Let's talk about this a little bit. X is usually denoted to be the variable, and in fact it is the variable. But for the purposes of this limit, what's changing is not x. What is changing?
H.
h is changing. So for the purposes of this limit, this is a constant value. Okay, now what's the limit of this quantity? Limit as h goes to 0 of cosine h minus 1 over h. 0. Plus. And what's, again, cosine x is constant for the purposes here times, what's the limit of this? 1. And what's the answer? Cosine x. Okay? So, and this is going to be an important rule. So remember this. The derivative of sine x is cosine x. Okay? You should be able to reproduce this. Okay, but you should also have this memorized so it's you can do your calculations quickly. The derivative of sine x is cosine x. And that kind of agrees with what I was saying here. What's the graph of cosine x? Well, it starts at 1 and then has the same period. So does that make sense? And that's the derivative of sine x, which is cosine x. That's why prime. It actually follows what we expected it to do. Okay. So you think you'll be able to do the derivative of cosine x? No, it's not a hint. Let's do it. Let's look at the derivative of cosine x. So cosine x prime would be cosine of x plus h minus cosine x over h. And once again, using the addition rule there, so cosine x cosine h minus sine x sine h minus cosine x over h. And we can use similar algebra here. Okay? In other words, cosine x is common to these two terms. You would say cosine x times the quantity cosine h minus 1 over h minus, we're talking about this term now, the limit is h goes to 0 sine x times sine h over h. So again, this would be cosine x times the limit of this quantity we said was 0 minus sine x times this quantity has a limit of 1. So what's the answer? Negative sine x. And that's the other quantity we should remember, that the derivative of cosine x equals negative sine x. Okay, these are very important. How many trigonometric functions are there? 6. The other 4 can be derived using, we don't have to go through the definition again. Sine and cosine are the fundamental building blocks of all trigonometric functions. So, in other words, every other trigonometric function is written in terms of sine and cosine. So using these facts in pink, together with the product and quotient rules, we should be able to calculate the derivatives. Okay? So let's calculate the derivative of cotangent. So to start, we're going to write this as cosine x over sine x. And then, since we know the derivative of each of these separately, we can go ahead and use the quotient rule. So I'll just write down the quotient rule now. Quotient rule says the top prime times the denominator minus the top times the denominator prime. Right? Is that clear? Over the denominator squared. Sine squared x. Okay, so let's do these primes then. Do it here. Cosine of x prime is what? Negative sine x times sine x minus cosine x times, what's the derivative of sine x? Cosine x over sine squared x. So let's rewrite this. They're both negative, so I'm just going to put a negative out here. And what do we get? We get sine squared x plus cosine squared x, which is 1. So the derivative of cotangent is negative 1 over sine squared. There's a special way to write this. Cosecant squared x. Okay. Cosecant is the reciprocal of sine. You remember? Okay. So then we can add to our list here of derivatives of trig functions. As a matter of fact, I'll write down the rest. So tangent x prime will be secant squared x, and cotangent x prime is negative cosecant squared x. The derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. And these are the derivatives of the 6 trig functions. Now, I don't know if I assigned this as homework or not, but you should probably be able to prove all these. Okay? The proof of the first two is rather long because it uses the definition, but the proof of all these comes from the simple differentiation rules, product rule, quotient rule, things like that. Okay? So tangent x is, of course, very, very similar to this. Okay? And you can still use the quotient rules for the other two. Because secant is a quotient of 1 and cosine. Okay? Any questions so far? Okay, let's put things together. Let's take a look at this. Look. Y equals x squared plus 3x times sine x. Now we can do derivatives of these very complex functions. Pretty sophisticated function. But calculating the derivative is not too hard. This is a product of 2 functions, so our derivative will be using the product rule. It means the derivative of the first times the second plus the first times the derivative of the second. Right? A direct application of the product rule. And then, so the derivative of this first term is 2x plus 3 times sine x. Keep this unchanged. And the derivative of sine x is cosine x. And that gives us our derivative. Okay? y is x squared plus 3 over tangent x. There are two ways to go about this. One way is to do the quotient rule. So I'll do that first. Okay. So that would be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. Sounds good? Okay. The derivative of x squared plus 3 is what? It's 2x times tangent x minus x squared plus 3 times the derivative of tangent, secant squared x, over tangent squared x. Good. That's your answer. Look at this limit. Yes?
One question, for the last problem, you said there was 2 ways to do it?
Oh, the other way, yeah. The other way would be to write this as x squared plus 3 times cotangent x, because that's the reciprocal of tangent, and then to use the product rule. Okay? That's the other way. Sorry. Thank you. Okay. Let's put that on hold. Let's say f of x equals secant x, right? How would you write down f prime of pi over 3 using the definition? Using the definition, that would be the limit as h goes to 0 of secant pi over 3 plus h minus secant pi over 3 over h. Right? And, well, we can make this theta, no? Nothing mystical about h. What's secant pi thirds? 2. 2. So then what is this limit? This limit is the derivative of this function at pi over 3. Okay? Do you see what I'm talking about? So this is the derivative of this function, right? When x is pi over 3. And the connection between limits and derivatives have to be done both ways. Okay? In other words, from both perspectives. From the perspective of trying to calculate a derivative, and from the perspective of trying to calculate the limit and relating that to a derivative. Right? F prime is a limit. Therefore, and then the other way to look at it is some limits are also representing derivatives. Okay? And to make that connection can simplify your work in calculating a lot of limits. So is that connection clear? Okay, great. So, what is the derivative of secant x? secant x, tangent x, when x is equal to pi thirds. So let's plug in pi thirds. That would be 2 times tangent of pi thirds is going to be radical. The answer is 2 radical 3. And that's the value of this limit, which would have been pretty complicated if you started doing things like 1 over cosine of this and then maybe doing the Hessian rule, and then that would be pretty tough. So the moral of the story is, if you're looking for the limit, and it looks like the limit for doing derivatives, it probably is the derivative of something. So take that into account. Okay, any questions about this? Yeah.
How would you know obviously what it is, but how would you know that it's equal to the secant?
Okay, well this looks like f of x plus h, right? Where x is pi root 3. It should be talking to you. It should say, Anna, that looks like secant pi root 3. Of course, if you know trigonometry, then that should be pretty, right? Because if I write something like this, then it's pretty clear that this is 3 squared, right? Yeah. So what is the function here whose derivative we're interested in? X squared, right? And what is the value of x that we're interested in doing the derivative for? 3. Okay? So this is actually the derivative of x squared evaluated at x equals 3. Okay? The derivative of x squared is 2x, evaluated at x equals 3. That's 6. And that's the value of this limit. Okay? Of course, this is useful here, but not really necessary because not too hard to do the square. Okay? But if we had something like this, that's 500. Then we would have an issue, right? 1 plus h to the power of 500 might take a couple of minutes to do it, right? And it's pretty long. So, but that's okay because we can recognize this. Maybe if you write this 1 as 1 to the 500, then maybe you can recognize that this function that you're interested in is x to the 500. And the specific point at which you're looking for the derivative is 1. Therefore, you can interpret this as the derivative of x to the 500 when x is 1. Or 500 x to the 499 when x is 1. And that's 500. Right? Okay. So, the definition of the derivative is that special limit that we have, and it's important to be able to translate limits that are that special limit back to the derivative, because the computations might be much faster. Here's another example. Okay. Anyway, that's h goes to 0, pi over 2 plus h times sine of pi over 2 plus h minus pi over 2 over h. Okay? So again, what happens if you let h go to 0? Let's just try to plug it in here. The numerator would be, this would be pi over 2, so sine pi over 2 is 1. This would be pi over 2. Pi over 2 times 1 is pi over 2. And then that would be 0 over 0, so we couldn't plug it in. But here's what we could do. If you write this pi over 2 as pi over 2 times sine of pi over 2, which is perfectly fine because that value is 1, right? We're not changing anything. Then you might recognize that this is the function that we're working with. And we're looking for the derivative here at the point pi over 2. Right? That's what this limit represents. I'm sorry?
Pi over 2 times sine of pi over 2. Where'd you add?
Well, this was like this. I just put times sine pi over 2. Because the value is 1. And it helps us see that this is the definition of the derivative. Okay, so this represents f prime, where that's f, evaluated at pi over 2. Yes? You see what I'm talking about? So then, okay, well let's figure out what f prime is. F prime, can we figure out f prime? Do we know enough? What type of function is that? It's a product, right? So that would be x prime sine x plus x sine x prime. And that's sine x plus x times the derivative of this is cosine x. Okay? So if I were to plug in pi over 2, I'd get 1 plus cosine pi over 2 is 0, so I just get 1. Okay? The alternative is pretty difficult, okay, to calculate this limit. All right. Let's take a look at this function. Y equals 2x plus 3 squared. And we want to calculate the derivative of this function. Okay. Well, this doesn't look like anything we know how to calculate the derivative for. So, but if I write this as a sum of powers, then we'd be okay. So I could actually write this out. 4x squared plus 12x plus 9. And now I can do the derivative very easily, term by term. Each one is just a power. So y prime would be 8x plus 12. Yeah? So for one, let's see, what is y prime of 1? 20, right? Okay. So keep that in mind. Let's think of y as a composition of two functions. Really, you can think of this as a composition of two functions. One of the functions being this 2x plus 3, and the other being a square function, right? So you can write this as f of g of x, okay, where f of x is x squared, and g of x is whatever's in the power, 2x plus 3. Right? Does that make sense? Okay. relate these individual functions that make the composite function, we want to relate the derivatives of those to the derivative of the original function separately. If I do the derivative of f, I get 2x. And if I do the derivative of g, I get 2. Right? Does that make sense?
Yeah.
Okay. And I'm interested in plugging what number here? 1. Okay. So let's calculate then, inside the g, I want to plug in 1. G prime of 1 is 2. G of 2, and G of 1 is what? 5. Okay. And then notice this. F prime evaluated at 5 is what? 10. Look at this. F prime of 5 is 10, and G prime of 1 is 2. What is their product? 20. That was the derivative of the original function. That's not a coincidence. As a matter of fact, let's write down what we just realized. Y prime was the derivative of f evaluated at 5. But what does 5 represent? 5 represents the value of g at 1. So f prime of g of 1, right, times g prime of 1. You see that? This was 10 times 2, just 20. And if you do some more examples of this, you'll see that this is an interesting observation, because there's actually a reason behind it. Right? What about that? 2x plus 3 to the power of 143. This method is promising. This method is not very promising for that question. Right?
Right.
So let's follow the same idea here. Think of this as a composition of two functions. One of the functions is a power function that goes to the power of 143. And the other is a 2x plus 3. Okay? So what this really represents is f of g of x. Okay? And if what I did there works, then I can very easily calculate the derivative at, let's say, 2. How would I do that? Well, according to this, okay, this is y prime of 1. According to this, what would I do? F prime of g of 2 times what? G prime of 2. So we need to figure out f prime, we need to figure out what g of 2 is, and we need to figure out g prime of 2. Okay, well, f prime is not hard. It's 143 x to the 142. And g prime of x is 2. Right? We also need g of 2. What's g of 2? 7. Okay, so let's work this out. So you want to do f prime of 7. G prime of 2 is what? Well, g prime of x is 2, so at any x you have 2. Yes? And f prime of 7 just 143 times 7 to the 142 times 2. And that's the answer. That's not a small number, but who cares? We have an answer. Okay? So this, if this were true, I don't even know if this is true yet, but if this is true, then this is going to open up so many opportunities for simple calculations of composite functions, functions composed of two simpler functions. Okay? And this is the subject of the next section. Okay, the chain rule. The chain rule will help us differentiate composite functions. And I'm going to write it in two different ways. First, what we've been saying is the derivative of a composite function is f prime evaluated at g of x times g prime of x. That's what these calculations suggest, and that's actually true. Another way to look at it is like this. If I have y as a function of u, and then u in turn is a function of x. So y is a function of u is a function of x. Then y ultimately depends on what? X. Y depends on u depends on x, so y ultimately depends on x. So I'm probably going to want to be able to calculate the rate of change of y with respect to x, because that's the independent variable. And according to this rule, what I could do is I could just take the derivative of y with respect to u times the derivative of u with respect to x. Okay. Y is a function of x, and x is a function of t. And we want to find dy dt. So how could we apply that notation here, that rule? We can't differentiate y in terms of t yet, because we know how y looks in terms of x. So we could do the derivative of y with respect to x times, see how x changes with respect to t. And that would give us our derivative. What's the derivative of y with respect to x? 2x. Times, what's the derivative of x with respect to t? 3. Okay, so that would be 6x. Except when I want to see how y changes with respect to t, I probably would find it more useful to change everything in terms of t. 6x, well, we have x here. 3t minus 4. Okay? depends on x, x depends on theta, so y ultimately depends on theta. And the relationship between all those derivatives, dy d theta is dy with respect to its immediate variable times the change of that, the rate of change of that variable with respect to theta. And the different ways I'm explaining, or I'm referring to these terms, are just different perspectives of the same thing. Okay, what's dy dx? We have a problem here, right? Because y itself is a composite function, right? Okay? So how would we do that? What is, if we were looking at this in terms of f of g of x, right? What is your f here? Cosine of x. And what is your g? 3x minus c. So according to the rule, I have to do f prime, leaving the inside the same, right? F was cosine. What's the derivative of that? Negative sine. Leaving the inside the same. Times g prime. This was g, so what's g prime? 3. Okay. Now that's just dy dx. Okay? Now times dx d theta. That's 2 theta. Yes? Okay, now putting everything together with negative 6 theta sine of 3 times theta squared minus 8 minus 8. And that's dy d theta. Okay? V equals pi r squared h. H is constant. R is a function of t. I don't know what it is, but I know it depends on t. And we want to know dv dt. Before we calculate this, let's see what's happening here. This models the volume of a cylinder, right, circular cylinder, with a constant height, but where the radius is variable, right? So constant height. And of course, when the radius changes, the volume changes, right? But the radius is changing with time. We don't know how, but it's changing with time. And so if I want to do a rate of change of volume, I need to know how it's changing with time. Okay? So one way to think about that is, let's first figure out how fast the volume is changing with respect to a changing radius, right? And then factor in that the radius is also changing with time, so we have to multiply that by dr dt. Okay? And then, okay, so dv dt, dv dr, okay, so again, h is fixed, so treat it as a constant. Pi is a constant. And what's the derivative of v then with respect to r? 2 pi rh. Okay, that's dv dr. Times, what's dr dt? Well, I don't know, right? Because I don't know what r of t is, so we just write dr dt. And that's the answer. Okay? So how fast the volume changes with time depends on what the radius is at that moment and how fast the radius is changing. Right? If the radius is changing really fast, right, then we expect the volume to be changing fast. Right? So these are the types of calculations we're going to do in the lesson called related rates of change. But the idea is that the rate of change of volume with time is related to the rate of change of the radius with time. Okay? And we're going to see more of those interactions. When we come back from the break, I'm going to do some more calculations with the chain rule to practice, and then we're going to do a clever application. Okay, so let's do a direct application of the chain rule. Now, the chain rule as written talks about how to do derivatives of composite functions with two functions. But some composite functions are composite functions with three functions, so f of g of h of x, something like that, okay? And the chain rule just follows the same kind of pattern in telling us how to do derivatives like that. So there's an interpretation of the chain rule called the outer inner rule. Okay? And the best way to understand the outer inner rule is to try to figure out the outermost function when we're working with composite functions. Literally, the outermost function in this expression is cosine x. The next function in is the power function. Okay? And the next function in is 3x plus 2. Okay? So thinking about these as layers. Right? And the way we differentiate composite functions, you can just think about differentiating the different layers one at a time. Okay? And this is my favorite part. Chain rule. Okay, basically, peel it like an onion. Okay? You know what an onion looks like? It's got layers. The only way you can peel it is from the outside in. Right? And so when we're talking about taking derivatives, peel it like an onion means just take the derivatives of the outer layer, and then the next layer inside, and then the next layer inside, and you multiply those derivatives together. Okay? So having said that, let's think about the derivative. So first, the outermost layer is cosine, and the derivative of cosine is negative sine, leaving the inner part the same, times the derivative of the inner function. Now the inner function is something to the power of 3. So then we would have to do the derivative of a power function, so the power rule. So that would be 3 times something squared, leaving the inner part the same, times the derivative of the innermost layer, which is 3. Okay? So before you do this though, you have to go back and try to understand how your function, what the outermost function is, what the next function in is, and what type of function the function within that is. And then simplify the rest. Let's look at another one. Let's look at y equals 3 sine squared of cosine of 4x minus 1. Okay? So here, let's think about this. What is the outermost layer? Is it sine or is it squared? Square. It's a square, right? Okay, maybe it might be, the 3 doesn't matter because it's just a constant. So we could write y as sine squared is sine of whatever squared. That's another way to write it. So now writing it this way, we can see clearly that the outermost function is what? The square function, the power function. Okay. When we have to do the derivative of a constant times a function, we can just rewrite the constant times the derivative of that function. So the way I think about this is, the derivative is, what's the derivative of bracket squared? 2 brackets. 2 brackets. Okay, to the power 1. Derivative of bracket squared is 2 times bracket to the power 1. Right? That's the power rule. Keeping whatever's in here the same. Times the derivative of sine. The derivative of sine something is cosine something. Keeping the inner part the same. Times, okay, so what was this? This was the derivative of sine, right?
Yes.
So now times the derivative of whatever's in that. Derivative of cosine is negative sine. Keeping whatever's inside that the same. Times the derivative of whatever's inside that, which is 4. Okay? Is that clear? So figuring out the outer function and then the next function in that and so forth is pretty important. Any questions about this example? Okay. Let's look at some quick recap of the rules that we had, the power rule, well, the power rule specifically, and let's try to figure out the general formula for it. In other words, if I have some function u of x, okay, what does the chain rule tell us about how to take the derivative of the function to the power n? Well, the derivative of that is going to be the derivative of the power rule, n u to the n minus 1, times the derivative of the function inside the power, which is u prime. This is called the generalized power rule. Okay? And this is important to remember. A quick application of this would be the derivative of 2x plus 3 to the power 10, where u is 2x plus 3. So that would be 10 2x plus 3 to the power 9 times the derivative of u, which is 2. Okay. Basically combines the power rule and the chain rule in one property. Earlier, I told you to memorize this derivative. Remember what it was?
Negative 1 over x squared.
Very good, negative 1 over x squared. So if you have u as a function of x, then the derivative of this expression is negative 1 over u squared times the derivative of u, which is u prime. So a generalized formula for the reciprocal of a function is negative u prime over u squared. And this saves a lot of time for calculating derivatives of functions that look like 1 over 3x squared minus 2, for example. So the derivative of that, you can think of this as u. And the derivative of that will be negative u prime, the prime of this denominator, which is what? 6x, divided by this u squared. Which is much faster than trying to do the quotient rule here, right? So I'd like you to commit this to memory. Another derivative that constantly appears in your calculations is the derivative of the square root of x. So if I write this as the derivative of x to the half and use the power rule, what do I get? 1/2 x to the negative half. And that's equal to 1 over 2 square root of x, right? Does that make sense?
Yeah.
So then the generalized version of that rule, okay, let's replace x with the function u. So the derivative of the square root of u would be 1 over 2 square root of u, okay, that's the rule, times u prime, times the derivative of the inner function, right? And then if you put this together, it's just u prime over 2 square root of u. This is very commonly occurring, okay? Is it clear how we get this u prime here? Why we get that? Okay.
No question. Question.
Yeah.
Okay, for that problem with 1 over u,
Uh-huh.
it was u prime over u squared, right? So if it's radical u, then wouldn't it be radical u squared, which is just u?
Over here?
Yeah, like if you were to compare it to the radical u prime.
Yeah, yeah. But then u prime would be a little different. U prime would have to be replaced by this. Okay, if you want to combine those two formulas. Let's do an example for this. So, like the square root of sine x, the derivative of the square root of sine x. Okay? So here, what is u? U is sine x. So in the numerator, you want u prime, and that would be cosine x. And in the denominator, you want 2 times the square root of u. So 2 times the square root of u. You're with me? Okay. Let's do another one. So the square root of x squared minus 3x prime. Again, u is this quantity in here. So u prime would be on the numerator, and the denominator is 2 square root of x squared minus 3x. Yes? find the equation of the tangent line to the curve x squared over, or x squared plus 2y squared equals 1 at the point let's see here, 1 over square root of 2, comma, 1/2. Okay? Find the equation of the tangent line to the curve x squared plus 2y squared equals 1 at the point 1 over square root of 1/2. Okay. So, well, what do we need to get the tangent line? We need the slope, right? We need the slope at 1 over square root of 2 1/2. Well, let's take a look at the picture. What is the picture for this? You've all taken conic sections. What is the curve? Ellipse, right? Maybe it would be simpler if you wrote it this way. Yeah? And how is it extended? In the horizontal or vertical direction? Horizontal? So I'm going to exaggerate this, but centered at 0, 0, right? Where's the point that we're interested in? Roughly. About here somewhere, right? Okay. So what do we expect the tangent line to look like? Maybe something like this. So this is the line that we're looking for. We want the equation of that line. But this problem is very different than the other problems we've done tangent lines for. The problem is finding the derivative, right? I mean, if you have y equals to, if you have y equals something, then you can get the derivative. But here we don't have y in terms of x. Right? This is an implicit equation. So the natural thing to do would be to solve for y. And if you solve for y, what do you get? You get 1 minus x squared over 2 square root of that with a plus minus. Right? Well, if we think of this, why do we get plus minus? Well, we get the top part as y is plus square root. And then we get the bottom part as negative square root. Right? But our point lives in the top, so we could use this function to represent the top part of the curve. Okay? So then from here, we're going to need to calculate the derivative so we can get the slope. Now let's use the rule I just wrote down. The derivative of a square root function, the square root of u was u prime over u, right? So over 2 times the square root of u. And the numerator was the derivative of this, right? The derivative of this would be negative x. That makes make sense? Okay, good. And so I want the slope at that point, and that point is when x is 1 over square root of 2. So the slope for the tangent line will be the derivative evaluated at 1 over the square root of 2. So I'm just going to plug that in here. Negative 1 over the square root of 2. 2 times the square root of 1 minus a half over a half. Right? So this would be negative 1 over square root of 2. This part isn't too bad. 1 minus a half is half. Half of that is a quarter. The square root of a quarter is half times 2 is 1. Right? You with me there? Well, you work it out, it's not that bad. So that's the slope, right? That's the slope. Are we done? Do we need anything else to write the equation? How do we write the equation? Tangent line? What's the formula? Y minus y1 equals the slope x minus x2. Right? That's a lot of work though for this simple problem, right? I mean, find the tangent line, it's an ellipse tangent. It shouldn't take this long. And we got lucky because it wasn't too hard to get y in terms of x. Okay? Well, thinking about y as a function of x, we can use the chain rule to do the derivative. Okay? Here's what I mean. Let's take a look at this. What is the derivative with respect to x of f of y? Okay? Y is a function of x. So how would we do that? Using the chain rule. What's the outermost function? F. So you do the derivative of f, keeping the inside the same, right? Times the derivative of the inside with respect to x. Times dy dx. Does that make sense? So, let's do an example. The dy dx of y squared. What is the outer function here? Square function. So I would, what's the derivative then? 2y. Times the derivative of the inner function. Y is a function of x. Okay, so what's the derivative of y? Y prime. Is that clear? Let's do one more. d by dx of sine y. What's the outer function? Sine. So this would be cosine y times y prime. Does that make sense? Okay, well, if we can do that using the chain rule, then you don't have to do any of this. The reason we did this is because we wanted to solve y in terms of x, so we could get dy dx, right? But we can get dy dx other way. Let's do the same problem. Find the equation of the line tangent to the curve x squared plus 2y equals 1 at the point that I gave earlier, 2y squared. Okay? So let's calculate derivatives with respect to x. X squared plus 2y squared equals the derivative of y. Okay? The derivative of the sum is the sum of the derivative. So what's the derivative of x squared? 2x. And what's the derivative of 2y squared? 4y times y prime. Okay? And what's the derivative of 1? Again, what I'm looking for to get the slope is y prime. So can I solve for y prime? So I can solve for y prime, and I get negative 2 over, negative x over 2y. Okay, but then you say, well, wait a minute, y prime is not a function, is not in terms of x alone. But that's okay, because I'm told I want the slope at this point. Okay, the slope at this point. In other words, I want y prime evaluated at this x value and this y value. So this expression is perfectly fine. Negative x over 2 times y, which is negative 1 over square root of 2, as before. Right? With much less work. This is the arithmetic required, which is much less. And like I said before, for this example, we were able to solve for y in terms of x here because it wasn't too difficult. But sometimes it's really, really difficult and even impossible. Here's such a situation. X cubed minus x plus y cubed plus 2y squared minus y is equal to 3. Okay? And I want to find dy dx. Or you can write that as y prime. Okay, and to do the old method, which was try to get y in terms of x and then differentiate that, is impossible here. Actually, it's not impossible, but if we were to actually solve for y, we'd get an expression that would not fit on this board. Okay, so for practical purposes, it's impossible to solve for y. But using this technique and thinking of y as a function of x, and using chain rule in a very clever way, we can find dy dx. So we want to take the derivative with respect to x. Okay, and the common pitfall when you're doing this in practice is people forget to take the derivative of the right-hand side. Okay? But if two quantities are equal, the rate of change of those two quantities is the same. Okay? So it doesn't make sense to take the derivative of one side and not the other. If this is equal to this, then this changes as fast as this changes. Right? So that's important. Again, this is pretty simple. This is just a sum or difference of some functions. So take the derivative of term by term. 3x squared minus 1. This is a function of x. So 3y squared y prime. This one is 4y y prime minus the derivative of 1y is y prime. Equals, the derivative of 3 is 0. And what am I looking for?
Y prime.
Y prime. This is where y prime lives. So we can throw the rest on the other side. I can write this as y prime times quantity 3y squared is 4y minus 1 equals 1 minus 3x squared. And then y prime would be 1 minus 3x squared over that. Okay, so we have the slope at every point xy. right? This process, this application of the chain rule has a name. It's called implicit differentiation. Okay? It's called implicit differentiation. Implicit because the function y is defined implicitly in terms of x, versus explicitly would be something like, y equals to 3x squared. That's an explicit definition because y is isolated. Okay? But here, y is defined implicitly, and so that's why it's called implicit differentiation. But don't think about implicit differentiation, okay, without thinking of the chain rule, because that's exactly what it is. That's all it is. And that's why I didn't want to name it when I was working. It's just all part of the chain rule. Okay, that's all. It's just an application of the chain rule. There isn't much new theory behind it. Okay? Right. Find the points on the circle x squared plus y squared equals 1 where the slope is 1. Now let's see if that makes sense. So this is the unit circle centered at the origin. And we know what a line tangent over a line with slope 1 looks like, right? So perhaps we expect it to be somewhere here and somewhere here. And so what we're doing is we're looking for these 2 points. When we say points, we mean both x and y coordinates. Okay? So how would we start? So we're going to say that the slope equals 1 in terms of derivatives is saying we want the derivative to be 1. That's what we want, right? You with me? Raise your hand if you're awake. Very good. Some of you didn't raise their hand. That scares me. Okay. So how do we get dy dx? Well, differentiate the equation. So here the derivative would be 2x plus 2y equals 0? 2y prime. Okay. So y prime is negative x over y. Okay? And we want that to equal to 1. We want to know what should x and y be so that this quotient equals 1. Okay? So this translates to negative x over y, which is the expression for y prime, equal 1. Give me 2 numbers that that's true for. Negative 1 and 1, right? here's where negative 1 is. Here's where negative 1 is. Right? That doesn't make any sense. That point doesn't make any sense because it's not even on the curve. Right? You want to point on the curve where the slope is 1. Okay? How would we guarantee that the point we're talking about is on the curve?
Y has to be less than
Well, yeah, x and y are to be less than 1, right? But there is a more concrete way of guareteeing that. We have to make sure that x squared plus y squared equals 1, right? We also have to make sure that the quotient of x and y equals 1. Well, negative the quotient. So those two together will give us our points x and y. Let me show you. So this is what we want. This is the same as writing it that way. Negative x over y equals 1, or y equals negative x. And the other equation was, right? Okay. Solving a system of equations graphically represents what? So this is from basic algebra. Graphically, what does it represent? Intersection points, thank you. So this represents the circle. What does y equal negative x represent? Represents a line, right? So we're looking for these two intersection points. Those are the points where the slope would be 1. Well, there are many ways for solving a system of equations. One way is the substitution method, right? So, do you want me to solve it, or is it clear? It's clear, right? Well, the two solutions would be negative 1 over square root of 2 and 1 over square root of 2. And the other one would be 1 over square root of 2 minus 1 over square root. Okay? Those would be the two solutions. And you can find out by substitution. Okay. Here's a curve. And these are pretty sophisticated curves. We'll graph them next time when we go to the lab. Okay? But at least we can do some calculations now. This is going to take some room. Okay, so the derivative of the left-hand side equals the derivative of the right-hand side. The derivative of the left-hand side is two terms. So we can do the derivative of this one separately first. This is a product. Okay, so we have to use the product rule here. The product rule says, take the derivative of the first function, keeping the second one the same, plus keep the first function the same, and take the derivative of the second function. This is a composite function. The outer function is sine, the derivative is cosine, times y prime. Okay? That's the derivative of first term, plus the second term also happens to be a product. The derivative of the first, keeping the second the same, plus keeping the first the same times the derivative of the second, which is negative sine x. I should put the negative here. Okay? And that's the derivative of this. Okay, equals the derivative of 7, 0. Alright, so our goal is to find dy dx, or y prime. So, what terms have that? These two. Right? So, everything what's in the box can move to the right-hand side, so I can have y sine x minus 2x sine y. And for the box, we can factor out y prime. Get x squared cosine y plus cosine x. And so y prime, the y sine x times 2 sine x is 2x sine y, x squared plus cosine